All right, the screencast is for Sarah. All right, we are on graphing rational functions. Yeah? Okay, cool, fun. So, when we're graphing rational functions, there's really 5 things we have to do, okay? We have to find the domain. I have to find any vertical asymptotes. I have to figure out if there's any horizontal asymptotes. See if there's any x-intercepts, and see if there's any y-intercepts. So there's 5 things we have to find. Secretly, there's a 6th thing, all right? We have to find out, are there any holes, right? Removable discontinuities, throw back to chapter 1 when we talked about that, holes, but not yet. So there's 5 things we have to find. The first thing you should always do in graphing, factor out your rational function. Make sure nothing cancels. Because if we have a factor on top and bottom that cancels, what is it? It's a hole. Wonderful. This is why I was harping on it so much in chapter 1, because this is what people missed last year, right? It sucked. I felt so bad. So I want to make sure you understand that this year. So we have x plus 1 on top, and then the bottom is a Vanna White time, blank of blank. Difference of squares. Yes, Rocky. Difference of squares. Difference of squares. So to factor it, it's just x plus 2, x minus 2. Difference of squares. You should know what that means. Because I like difference of squares. They're super easy to factor. Okay, so nothing cancels. All right, that's fine. That means we don't have any holes. No surprise. We will have a hole in the, I don't know, in a page and a half or something. Yeah, example, what is it, D? Whatever. Nothing cancels. So let's talk about the domain. How do you find domain of a rational function, right? Chapter 6, so 1, chapter 1. Chapter 1, how do you find domain? I think you said it. Yeah, set the denominator equal to 0. Well, I factored it. It makes it finding really easy, right? That means you set each of these equal to 0, x cannot equal negative 2, and x cannot equal 2. Because if x equals 2, the bottom goes to 0, and our whole function is undefined. So imagine you have a giant piece of paper with like a bunch of numbers, and you only want to cut out 2 and negative 2, and then tape all the rest of the paper together. That's literally what we're writing when we write domain. I want all the numbers except negative 2 and positive 2. Oops, I kind of ran into that, sorry. I think you can read it. That's the domain. So question, don't say this out loud. How can I find the vertical asymptotes, right? Don't say it out loud, but how can I find the vertical asymptotes? So turn to the person next to you. How do I find vertical asymptotes? Okay, cool. I heard a bunch of different people say the answer. It's the same as what we just found. It's negative 2 and positive 2. Yeah, because remember, we factored it first to see if anything canceled. If it canceled, that's a hole. Nothing canceled. So both factors on bottom, when I set them equal 0, that's where my vertical asymptotes occur. So it happens at x equals 2 and at x equals negative 2. Ooh, hard one. Horizontal asymptotes. Horizontal asymptotes. So there's a special kind of thing we use to find them. It's called the blank blank test. Leading term test. Awesome. So let's find our leading terms. The things with the highest exponents. Check it out. So this is what you must write. I don't know another way to say this except if you don't write it exactly, you'll get a point off. Okay. So you have to write limit of f of x, limit as x approaches infinity of the leading terms. Now, x over x squared, that's something you can simplify. Sorry, can you see in the back? You can simplify it. Okay, so you simplify it. This is going to be the same thing as limit as x goes to infinity of 1 over x, right? Because one of the x's cancel out. So think about what happens, right? So this is intuition, right? You kind of have to like imagine what's going on. As x goes to infinity, okay, as it gets really big. So as x gets bigger and bigger, I'm dividing by a bigger and bigger number, right? 1 over 2, 1 over 3, 1 over 4, 1 over 5. What's happening to my overall number when I'm dividing by a bigger number? It gets smaller, it gets closer to 0. Bigger on bottom, it goes to 0. Okay.
Do you not say limit equals?
Yeah, there you go. 0. So I would write this as y equals 0. So I have a horizontal asymptote at y equals 0. Vertical asymptote at 2 and negative 2. On your practice test, you see how I like set up this problem. I literally give you a line, and you should write y equals 0. I'm asking for the horizontal asymptote. It has to be a line. That's why you say, oh, y equals 0, because that's a line. Okay. Are we okay so far? Any questions? Yes?
Can you explain again why equals 0?
Okay, yeah, because as x gets bigger, we're dividing by bigger and bigger numbers, right? 1/2 is bigger than 1/3, 1/4, 1/100th. I'm dividing by bigger and bigger numbers, which means the overall number is getting smaller and smaller. Now imagine 1 over a million. That's really, really small. 1 over a trillion billion, right? That's really, really small. So I'm getting closer and closer to 0. So bigger on bottom gets closer and closer to 0. Okay, so we're going to deal with like other examples as well. So think about how we would find the x-intercept. So x-intercept is when y equals 0. This is when y equals 0. So I'm going to come up here, and I want to make sure we're like paying attention. Okay, so what happens if the top of this rational function equals 0? 0 divided by a number is equal to? 0. Okay. What happens if the bottom is equal to 0? A number divided by 0 is undefined. Okay, so that's important. To find the x-intercepts, you set the top, the numerator, equal to 0. So we are setting the y equal to 0, right? So we have 0 equals, you set this equal to 0 because if the bottom equals 0, it's no bueno. Y will only equal 0 if the top of my fraction is equal to 0. Does that make sense? I'm going to have to think about another way to explain it. Y, the only way the right side can equal 0 is if the top's equal to 0, because I'm setting the left side equal to 0. If this is 0, the only way the right side can equal 0 is if the top is 0. Because if the bottom's 0, it's undefined. Okay. So I set the top equal to 0. I solve and I see that x is equal to -1. And since I want an intercept, that's a point. So it has to be an x comma y coordinate. -1 comma 0. Secretly, I'm writing all of my information like close to the right side, so when I scroll over, I can still see my info and I graph. That's why. You don't have to space it out so much. Okay, so the y-intercept is when x equals 0. This one's a lot more chill to figure out because all you do is just plug in 0 for x. So I have 0 plus 1 over 0 minus 4. So that's just -1/4. So I have all of my information, right? I have my asymptotes, my intercepts. The next step, the next step is to just put it all on the graph together. So I have a asymptote at -2, so I draw a vertical. At +2, I have a vertical asymptote. Ooh, that's bad. +2, vertical asymptote. I have a horizontal at y equals 0. So it's kind of going to be hard to see, but this is where it is. Yes? Oh, yeah, of course. Think I can make it? Oh, I'm going to hit someone in the face. Ready? Okay, ready? Hey. Baller. Okay. No, I used to do shot put and discus. So like, yeah, in high school, yeah, I went to state like multiple years.
What did you do?
Yeah, shot put and discus. Shot put, you like throw an 8-pound ball. Discus is like 2 pounds and you whip it out there. Yeah, I know. It's a shock. It's a surprise. I actually used to be athletic. Surprise. Yeah, okay. It's all good. This is what happens when you're an adult. It sucks. But then I tore my labrum in my shoulder, so that's why when I go and shoot basketball now, it's weird because my muscle memory doesn't match up with what's in there. I have titanium screws in my shoulder. That's really personal. Okay, let's keep going. I literally have titanium screws, yeah. Okay, cool. Random facts. Let's keep going. What? Yeah, this is great. Sarah, what's up? Okay. Okay, let's do this. All right, so I have a couple points. I have an x-intercept, -1, 0, and 0, -1/4. So that's about right here. So I'm gonna warn you. Actually, pause. Did you learn about horizontal asymptotes last year? Yeah, they're flaky. They're so flaky. I literally hate them. Vertical asymptotes, they're law-abiding citizens. You never can cross a vertical asymptote, right? It's like the mafia. You never cross them. But the horizontal asymptotes, it just depends. So remember how we found horizontal asymptotes? It's the end behavior. So really, the only time you can't cross a horizontal asymptote is when you're like near the ends. Whatever happens in the middle, right? That's why they're flaky, is because we're going to cross the horizontal asymptote. But it only happens if you have, it only can potentially happen if you have more than one vertical asymptote. I know, it's so dumb. I hate them. They're flaky, non-reliable, only at the ends. So that means, I know, whatever. You probably, I know, you learned about last year. It just sucks. So notice this part in the middle. There's a dot right on the horizontal asymptote. What the heck? It's so dumb. It's so dumb. Like, why? Don't call it an asymptote if you cross it, right? Call it an asymptote sometimes. That's all I call it. So this is a horizontal asymptote sometimes. Sometimes we can cross it, sometimes we can't. We only can cross it if we're like in the middle between vertical asymptotes, but you can't cross it if you're at the ends. I know, I don't like it just as much as you. But this middle part, let's figure out what's going on here. So these are my two intercepts, and I want to connect them, so I'm just going to make a little line. But you have to continue the line. So I see that I'm like coming down this way, so I'm going to continue this and going up. Right, you just kind of, you follow the asymptotes, follow the asymptotes. So here's our predicament. I either can continue up, or this can go down. I have to figure out which way it's going. Okay, so the best way to do that is just plug in a number. Right, all I care about is it greater than -1/4, because that's the y value. Am I coming up, or am I coming down? And that tells me which way I'm going. So I'll plug in.
Does the exponent not decide?
It probably does, but it's just easier to plug in. Yeah, because it's, to me, that's a lot quicker. I don't know, you do you, man. If you find a shortcut, that's cool. Yeah. I'm gonna plug in 1. Just plug in 1. F of 1. So this is 1 plus 1 is 2 over, let's see, 1. So I'm plugging into this right here. 1 plus 2 is 3 times 1 minus 2 is -1. So this is 2 over -3. Oh, so -2/3. Am I above or below -1/4? I'm below. Okay, so it's about right here. So it is going to be going down. Ready? You just connect them and follow the asymptote.
Wait, so if it's greater than 1/4?
Greater than -1/4, because that's the y value of this guy right here.
Yeah.
If it was like, oh, positive, then it would come up. That's how I'm deciding how to graph it. What's wrong? You okay?
I was trying to figure something out. I don't know.
That's fine. Okay. So now we have to graph the rest. I know, it sucks. Okay, so we have a 50-50 shot. Ready for this? Either our graph's going to look like this, or it's going to look like this. We have to decide which one it is. So I'm going to plug in 3, right? I just have to plug in a number to the right of my asymptote, x equals 2. So I'm going to plug in 3, f of 3. Maybe it would be easier to plug in this one. Whatever, either one works. It's the same thing. 3 plus 1 is 4 over 3 squared is 9 minus 4 is 5. Is 4/5 above my horizontal asymptote or below? Above, because it's positive. Surprise. Okay, guess what? I have a point here. Follow the asymptotes. That's it. I can't cross my vertical, and now, guess what? I'm at my end. Here's my end behavior. Oh, I can't cross my horizontal now.
Does it matter like if you're playing?
Well, you have to like figure out which way it is.
But like,
You have to figure out if it's above or below.
about like 3 1. Like, how do you get 3
Oh, this guy right here?
No, like your point, like on the graph.
Yeah, 3, 4/5 is about like 0.8. It's like between 0 and 1. I mean, here what I care about is, are you above or are you below? And I just want to see like this little boy right here that tells you above. It proves it. Yeah. Especially because I'm going to let you guys use your like actual calculator, not scientific. And you'll be able to graph and like see. I need to see the work. I have to see this work since I am letting you use your whole calculator. You have to. I got to see this. I'm telling you right now, points off if I don't see you plugging in a number. Cool. I don't know like clearer way of saying that. Yeah?
Do we also have to do the left side or is it only
Yes, we're not done. We got to do the left side too. Okay, making sure we drew it. I just need to plug in a point. I'm going to plug in -3. What? Make yourself a note. I'm not your mom. I already tell you guys so many things. Like, oh, hey, guess what? Alex initial knowledge check due tomorrow. And I put everything on my jag for you. Tomorrow. Not tomorrow. Friday. Yeah, Friday. Okay. Okay. Got you. I got you. Got him. Okay. -2/5. So that's negative. It's below. At least I know who didn't do it based on the gas. Okay. Cool. So that's what it looks like. You plug in your calculator, it'll literally show you. So that's the reason why I initially wasn't going to let you use your calculator. But whatever, don't make dumb algebra mistakes with like adding and subtracting. So there you go, use your calculator. I want to make sure if you miss points, it's because it's the method and the stuff you're actually learning, not like pre-algebra computation. Okay, so guess what we're going to do for example B? The same thing. Okay, go ahead, give it a shot. I'm going to leave this up here if you're not done. Follow the same pattern. You'll have like a solid 30 seconds. I want to see everyone doing it. Remember, participation grade means you are in class, writing, paying attention. Now sleeping. Let's go. Right. Give it a shot. Whatever, okay. What's the first thing you do? Factor. Yeah, okay. Secretly, if you factor out the 2, it's a difference of squares on the bottom. Same domain as before. What? This graph? I mean, this one wasn't even on both sides. So, I mean, roughly it looks the same. Yeah. Okay. So whenever you have a limit and there's no variable in it, it's a constant number, the answer is just going to be that constant. So if I'm taking the limit of 5 as x goes to infinity, it'll be 5. Taking the limit of 7.8 as x goes to infinity, it's just 7.8. Yeah. Because if it totally cancels out, it's just the ratio of the coefficients. So I'm writing the solutions up here. Hopefully you've gotten most of this by yourself. If you have, then like give yourself a little pat on the back. Solid. There's two of them. Yeah, it's always the top. The bottom gives you vertical asymptotes, top gives you x-intercepts. So you can draw the asymptotes if you're done with the math, figuring those out. It's about maybe another 30 seconds or so, and then we'll go through how to graph it together. So it's a little difficult. Yeah. So you can plot your x-intercepts, the y-intercept, right? Because 3 over 2 is the same thing as 1.5. Another 10 seconds or so, and then we'll go over it. So, like the outside portions, like we know which side we're on already. That's pretty nice, right? We know, am I on the top, I'm on the bottom? Oh, JK, I have a point on the bottom, so I know I'm on the bottom. All right, lucky for us, this is a nice point. So you have to follow the asymptote. Since we are at the end behavior, it's like it's the outside portion. This one you have to follow the asymptote since we're on the, oh my god, it's not clear. No, since I'm below the horizontal asymptote, I know I have to stay below. Yeah. The middle is a little more tricky. I don't know. Maybe, maybe I could cross it this way. Maybe my graph will look like this. Maybe my graph looks like that. Maybe my graph looks like that. Right? There's 4 different options to like plug in a number. So I'll plug in 1, and I'm going to plug in -1. And all I have to know is like, okay, what's it gonna look like? This way, up or down. There's really 4 options. So plug in 1, -3 times 4 over 2 times -1 times 3. I'm just plugging into this guy right here. Makes the math a little easier. So this is just -12 over -6. What's -12 over 6? +2. Okay. So that means I have a point right here. Okay, so I know on the right side, this portion, it's going to be going up. Because I just have to follow, I connect the 2 points, and then I just like, keep going and follow the asymptote. Okay, 50-50 shot. We're almost done. Is it going to swoop up, or is it just going to continue down? Plug in -1. So I have -5 times 2 over 2 times -3 times 1. So -10 over -6. Ooh. I'll zoom in a little bit. I think we're close. Yeah, +5/3. What is this as a decimal roughly? 1 point, it's like 1 2/3, 1.66. What is this y value for the y-intercept? 1.5. So 1.66, right? 5/3 is higher than 3/2. So it's going to be about right here. So I know it's coming up as well. Cool. Sweet. Okay, so the next example, I'm cutting. Yeah, Honors does it, we're not. Cool. Oblique asymptotes, they're more of a pain than anything. So, also, I don't test you on it. We do about 2 less chapters than Honors Pre-Cal, and then sometimes in sections we like cut out certain examples. This is one of them I'm cutting. It's like, I mean, it's fine, but like, if you need to know it, you'll always go back and learn it. Like the next class that you would learn, you would do it. Also, I don't use it very much in calc, so it's useful. It's useful if you want to know about it. Go ahead and learn it, but I have to make sure I'm not treating you as honors. I gotta be fair. All right, here's for the main event. This is what we've been talking about for a while. When numerators and denominators have common terms which can be eliminated, removable discontinuities called wholes appear at the zeros of the common factor. So if there's a factor that cancels, that's where you have a whole. Cool. So we're going to do the exact same thing as before. Right, we'll find the domain, the vertical, horizontal asymptotes, x-intercepts, y-intercepts, and then we have to see where is our hole. If we have a hole, where is it? What's the actual coordinate? Because I got to draw a little donut, got to draw a little hole, so I have to know where to draw it. First thing we're going to do is factor this out. So difference of squares. So I have x plus 3, x minus 3 on top. The bottom, I have x plus 2 and x minus 3 on bottom. Factor it out. Ooh, we see something cancels. So this means hole. We have a hole at x equals 3. How did I know it was 3 and not negative 3, right? It's the x minus 3 that cancels out. Who knows? Set it equal to 0. Blessed. All right. Just pounding it into your brain because those are questions I don't want to answer. So I asked them to you so that way you remember. Okay, so let's go through and let's find everything. So domain, we know that x can equal 3 and x can equal negative 2. So I'm just going to cut those out. Negative infinity to negative 2. We still have to include all the numbers between negative 2 and 3, and then 3 to infinity.
Please don't count the x minus 1.
Because for domain, x equals 3 is still not in our domain. It's not a vertical asymptote, but it's still like the whole. It's not defined there. Yeah. So domain, you said the bottom, all the factors equal to 0. Yeah. Cool. All right, x can't equal 2, negative 2, and x can't equal 3. But vertical asymptotes, right? I'm like, oh, cool. I'm in a hurry, so I'm just going to write x equals negative 2 and x equals 3. Just kidding. This is a hole. You can't say that's a horizontal or a vertical asymptote. Too many times. Too many times. That's how many times people did that last year. Too many. Too many to remember. This is probably the top thing people missed on the Chapter 2 test last year. Factor first. Cancel out anything. You have to do that first. Okay, we only have one vertical asymptote. Let's go ahead. Let's do the horizontal. Horizontal asymptote.
Wait.
Yes.
Oh, wait, never mind. Yeah.
Find horizontal, do the leading term test. I forget how tricky I try to be. I think I pretty much leave them in order. Just make sure you grab the leading terms. Notice these have the same exponent, so it's just the ratio of the coefficients. Turns out the coefficients are both 1, so it's just going to be 1. 3 things down, 3 to go. Find our intercepts. Feel free to work ahead if you already know what you're doing. So our x-intercepts, this is when y equals 0. So you set the top equal to 0. But we already know x equals 3 is a hole. It's not actually going to be an x-intercept. So what you could do, what?
How do you negative 3?
If you set x plus 3 equal to 0, you get negative 3?
Would that mean
You
y
want-
equals 0?
Well, wait.
No, x-intercept is when y equals 0.
Do you not set the whole equation?
Oh, didn't you plug in 0?
No, because the y-intercept is when you plug in x equals 0.
But when you plug in x 0 equals 0, then you get negative 9 over negative 6.
Yeah, but that's for the y-intercept. Y-intercept's when x equals 0. The x-intercept's when y equals 0.
Uh-oh. Do we have to find these points?
You're required to find the x and y intercepts. Like, you have to. If you look at your practice test, like, that's on there, like, shows you. Okay, and then the very last thing, right? This is the extra part. Since we know we have a hole, I have to find the coordinate of the hole. Because I literally have to draw the little donut. I have to draw the hole on my graph. So we want to find the y value at the hole. So remember when we were studying discontinuities? And I was like, what is the limit? What is the y value? What are we approaching for the hole? So what you want to do is plug into the reduced equation, aka the one where the factors cancel out already. Because if I plug in 3 into my original equation, I get 0 over 0. That's indeterminate. It doesn't tell us anything. Since we know all that x minus 3 term does is cause a hole, I can cancel it out, and I'm going to plug into the x plus 3 over the x plus 2. Plugged into reduce equation. So plug in 3 and we get 6 over 5. Plug in x equals 3 and we get 6 over 5. So I'll have a hole at 3, 6/5. There's a lot of information we just found, and that's really all we need to graph it. So first, vertical asymptote at -2.
Yeah. How you got 6?
Well, plug in 3 into the reduced. This is the reduced equation. This is what we're left with after I cancel out the x plus 3 term. So if you plug in 3 here, 3 plus 3 is 6, 3 plus 2 is 5. Because I have a hole at x equals 3.
But why is that a hole?
Because the factors cancel out up here. It's the same factor on top and bottom, and it cancels. If you have a factor on top and bottom that cancels, that's a hole. It's a removable discontinuity.
But why is whatever left you plug in 3?
Because that's what the y value would be if it exists, but that's not what the y value actually is.
Okay.
Yeah. So, all right, so we're drawing our horizontal asymptote at y equals 1. And then I have all these points to put on there. I have a point at -3, 0. I have a point at 0, 3.5. I have a hole at 3, and then 6/5 is a little bit over 1. So 3 and just a little bit over 1, I have a hole. Can you tell the difference between my hole and my points? Yes. Okay. I only have one vertical asymptote. Right? There's no there's no flakiness with our horizontal. Because you have to stay on the side. So since I have a point, right, so I'm looking down here, since I have a point below my horizontal, I know I'm not able to touch it, so I come up and approach but never touch. So you just follow the asymptotes. Follow the asymptote up. Make sure you go through the hole. And we're good. That's it.
Would it ever be a time when you directly on the asymptote?
So the only times I can do that is if I have like more than one vertical asymptote, right? Because then I could cross it like I did here. So you only cross a horizontal asymptote if you have more than one vertical, because that's when you can cross. But if you only have one, like you can't cross. Because it's horizontal asymptotes can only be flaky if you're between vertical asymptotes. If you're near the ends, it's going to be a law-abiding citizen. That's it. Yeah. It's kind of like when you're driving on the 405. If you see a cop, you won't speed. But between the times you see a cop, oh yeah, you'll just floor it. There you go. Relatable. Let's keep going. I know you guys speed. About 2 years ago, maybe it was 3, there was a student who was like, I saw you on the 101, Miss O'Brien. I was like, I didn't see you. I saw you zoom by me. Speedier. Okay. Solving rational functions. So you've kind of done this before. It's literally solving things with fractions. So to solve a rational function, can I zoom down a little? No, I don't think we're done. To solve a rational function, multiply each term in the equation by the LCD, the least common denominator. of all the terms of the equation. Be sure to check for extraneous solutions, aka things that we're not allowed to have as x. So for instance, if I found a solution that was like 3, well, we just said 3 is like undefined, right? So literally whenever the bottom of your rational function is equal to 0, like that will be an extraneous solution. That was probably not clear. Let's actually do the example. So first, I want to know, what value of x can I not have? Yeah, right? You set this equal to 0, right? And we see x cannot equal 6. So that is our constraint, right? X cannot equal 6. Guess what happens if at the end we're like, aha, x equals 6? It's extraneous. It's wrong. Just kidding. We can't have x equals 6. That would be extraneous. Okay, now we need to find the least common denominator. One more time. Say it louder. X minus 6. Okay, least common denominator, x minus 6. So what we are going to do is we're going to multiply every single term by x minus 6. Or, I'm going to multiply every term by x minus 6. Guess what happens when I take 0 times x minus 6? Yeah, it's just 0, whatever. And then this one, it literally cancels out. Let me do that. Okay, this one, it cancels out, so I'm just left with the minus 4. But this other one, we have to distribute the x out. So I have x squared minus 6x minus 4 equals 0. Okay, cool. We can solve this out. Yes.
Wait, wouldn't wouldn't you put them both over x minus 6?
I multiplied them both by x plus 6. I multiplied every single term by x minus 6.
Then wouldn't it be x squared minus 6x minus 4 over?
No, because this canceled out. Do you see right here? It cancels out.
Why would you multiply it by itself?
I'm multiplying, okay, so you either can multiply every single term, because what you do to one side, you do the other. As long as I'm multiplying every term on the left and right side by the same number, x minus 6, I'm okay. So I'm showing you this way, because normally you'd have x minus 4 over x minus 6 equals 0, and like the way we normally do it is like, oh, okay, just multiply this by x minus 6 over x minus 6. And then they're over the same number, and then we ignore the bottom, because all that says is like, oh, if we're dividing by x minus 6, we just don't want x to equal 6. The only way the left side can equal 0, because the right side equals 0, the only way the left side can equal 0 is if the top of my fraction equals 0. Because if the bottom equals 0, it's undefined. If the top equals 0, it will be 0. The overall will be 0. But I'm trying to show you a good method of solving. If you multiply every single number by your least common denominator, certain things will cancel. This one, you could solve this one by doing what I wrote on the right side. Like, that's easy. But later when we have harder problems, you multiply every single term by least common denominator, it's just simpler. Okay, so ignoring this. So I want to solve this. What numbers add to negative 6 and multiply negative 4? None. What do we use? Quadratic. Okay. X equals negative b plus or minus square root b squared minus 4ac all over 2a. Okay, x equals 6 plus or minus, oops, forgot the square, 36 plus 16 all over 2. 6 plus or minus square root 52 over 2. So a deck of cards has 52 cards. How many suits? 4. How many cards in each suit? 13. Did you know 4 times 13 is 52? Now you do. Okay. Square root 52 is literally the same thing as saying square root of 4 times square root 13. Because 4 suits times 13 cards in each suit is 52 cards. Multiplication. Surprise, 4 is a perfect square. So square root 52 is the same thing as saying 2 root 13. And once I have that, I can divide every single term by 2. So this is 3 plus or minus root 13. Okay, here's my answers. We have to make sure they're not extraneous. Are either one of these answers our restriction? No, these are not 6. This is not equal to 6, so we're good. Those are our 2 answers. That's it. All right, and now B is where the real party begins. Oh, yep. It's great. So fun.
When's the test?
The test is scheduled for the 27th. Today's Thursday, 24, 25, Tuesday, Monday. Okay. Yeah. I need to look at my chapter 3 notes to see if it's even feasible. I have to have the chapter 3 test on the 13th because sophomores leave. I have to have that test before they leave. Yeah. So let me look tonight to see if I can actually compress anything. Otherwise, the test is going to be 27. What?
There are only 2 so far.
Yes. And I have to have the unit done before they leave. Cool. Okay, let's go on to B. So let's talk about the restrictions. Can I rewrite this? Yeah, what are these factors? What are the 2 factors? X minus 6 and x plus 3. Wonderful. Okay, so if I'm looking at all 3 of my denominators, what is the least common denominator? Yeah, exactly. X minus 6 and times x plus 3. While we're on the topic, what's the restriction on my domain? X cannot equal positive 6 and negative 3. Bomb. Yeah, exactly. So if I get an answer at the end where it's like, x equals negative 3, just kidding, that's extraneous, cannot be negative 3. We just said that. So we have our least common denominator. We know the restrictions. At the end, always just double check you didn't get one of your restrictions. I'm going to go through, multiply every single term by our least common denominator. Guess what? Things are going to cancel. So I take x minus 6 times x plus 3, and I'm going to multiply by 2x over x plus 3. And then I'm going to take x minus 6 times x plus 3 and multiply by 3 over x minus 6. Okay, and then take x plus 6 times x, oh my god, x minus 6 times x plus 3 and multiply by 27 over, well, it's literally our least common denominator, x minus 6 and x plus 3. Here's the fun part. Let's just cross out some stuff. Yeah, here we go. Wonderful. Makes it a little easier to deal with. So don't forget to distribute the 2x to each one of these, the 3 to each of these. So 2x squared minus 12x. After I write out this line, I'll pause for a second to make sure we're all caught up. Plus 3x plus 9 equals 27. Ideally, we'll get everything on one side, all like terms combined, and we can solve. So 2x squared minus 9x minus 18 equals 0. Okay, we'll pause there. Make sure we're all here. If you're here already, guess what we're going to do? We're going to solve, so go ahead, factor that boy out. All right. Give it a moment before I factor. Alright, I just did the case-if method, figure out what my factors were. Alright, so that's in blue, dealing with coefficients other than 1. Yay, okay. Set each equal to 0. So I see x equals negative 3 over 2 and x equals 6. Yeah, I'm good. All right, I got my answers. Let me just box them. I'm done with the problem. No, what do I need to do? Check for extraneous solutions. What were my restrictions? Oh my gosh, 6. That can't be an answer, so it's only x equals -3/2. Yeah. That's right, that's right. Here we go. Yeah. All right, so do you want to try the next one? We literally have like 1 minute, so great. The next one will probably take like 3 minutes, but we don't have enough time. Cool. So we'll definitely finish the rest of this tomorrow when I see you guys. It's an extended period. Okay, see you guys.